Looking for investment ideas? Get inspired by investors worldwide on eToro. Just choose your investors and copy their investment portfolios, their performances, their strategies, all yours for the taking. From now on, whatever they invest in, you invest in. So, be the
This college this
talk about a particularly convenient way to write down on these solution sets. That's called matrices and vectors. And so we'll see you next time when we talk about describing the solution set part 2. Whoops, there we go. It's describing the solution set part 2. Okay, very good. Bye-bye. Hi, hello, hi, how are you? So last time we talked about describing the solution set in the context where there are infinitely many solutions. I want to continue that today. Today I want to introduce a way of writing these things, both the linear systems and also the solutions, that saves a lot of the book to write down these solution sets. That's called matrices and vectors. And so we'll see See you next time when we talk about describing the solution set part 2. Whoops, there we go. It's describing the solution set part 2. Okay, very good. Bye-bye. Hi, hello, hi, how are you? So last time we talked about describing the solution set in the context where there are infinitely many solutions, and I want to continue that today. Today I want to introduce a way of writing these things, both the linear systems and also the solutions, that saves a lot of the bookkeeping burden, and also it will turn out add some conceptual meaning to the whole thing. So you may have seen matrices and vectors in another context. You might have seen it in a physics class, for example. At the moment, we're not interpreting it so much as the kinds of things you see in a physics class or a calculus 3 class. At the moment, we're just going to introduce them as a place to put numbers. That's all. But soon enough, we'll give them a more conceptual meaning. But at the moment, just simply a place to hold numbers. So an M by N matrix is a rectangular array of numbers. It's just numbers, no particular physical meaning. M rows, N columns. You read that aloud as M by N, always the number of rows first, because you got to put something first. You might as well always put the same thing first and be organized about it. The numbers in the matrix are called entries. So 3 is an entry, minus 5 is an entry, 6 is an entry. This is a 2 by 3 matrix, 1 row, 2 rows, 3 columns, 1, 2, 3. So 2 by 3. Always the number of rows first. You often name matrices with capital Roman letters. And then when you want to talk about the entries in the matrix, for example, the 4 here in the second row, first column, you often use the associated lowercase Roman letters. That's the convention that I'm going to be sticking to. Not 100% of the time, but 95% of the time we'll be writing here capital Roman letter for the matrix and lower Roman letter for the entry, and you'll often see that in practice, very often. Okay, a column vector is often just called a vector, is a matrix with a single column. If a matrix has a single row, it's called a row vector. And again, you may have I've seen these things where they have some meaning, and we'll get to those soon enough, but at the moment we're just simply using them as places to hold numbers. The entries of a vector are sometimes called components. Instead of entry up here, you often call it component, and the column or row vector whose components are all zeros is the zero vector, happens to come up a lot in practice. I like to denote vectors with an over arrow, with an arrow on top. So let me bring up my there we go, and bring up my.
How do you debug a slow web page and find the root cause? In this video, I'm going to reveal the best way to do this that will save you time and money, because time is money apparently. But first, when you discover a slow
My piece of paper here, and so I'll, whoops, a little shadow there. So I'll denote vectors. There we go. I'll denote vectors with an over arrow. In handwriting, I'll write something like that, V or W, something like that. Okay, so I'll denote vectors with an over arrow. Let me bring back to the. There we go. In the textbook, the over arrow is easier to read than my handwriting. That's just the way it goes. This particular column vector has 3 components: -1, -1/2, and 0. Oh, I should have mentioned, I like over arrow because you often see boldface, very often see boldface in other books, but I can't do boldface in handwriting or on a blackboard, so I like the over arrow and I put it in both places. But boldface is very common, very common. In fact, maybe more common than over arrow. So this is a row vector with 3 components, and this is the 2-component 0 vector. See a 0 with an over arrow. I put it. Can't do both. Off one. Expect that. Right. So I'll denote vectors with an over arrow. In handwriting, I'll write something like that, V or W, something like that. Okay, so I'll denote vectors with an over arrow. Let me bring back to the, there we go. In the textbook, there's the over arrow is easier to read than my handwriting. That's just the way it goes. This particular column vector has three components: -1, -1/2, and 0. Or I should have mentioned, I like over arrow because you often see boldface, very often see boldface in other books, but I can't do boldface in handwriting or on a blackboard. So I like the over arrow, and I put it in both places. But boldface is very common, very common. In fact, maybe more common than over arrow. So this is a row vector with three components, and this is the two-component 0 vector. See a 0 with an over arrow. Oops. I'm going to want to be able to add these and to scale and to rescale them to double them or triple them. So I need to define those operations. So this says if you have two vectors, u and v, then you can add them by adding the components. You notice, don't you, that this says down to un and this says down to vn, so they are the same size. If this one has 5 entries, then this one has 5 entries also. Anyway, if they have the same number of entries, then you add just by adding the components. And you can also rescale the components. That's called a scalar. Multiplication of the real number r. In this context, r is called a scalar. And if for example, you want to multiply the whole vector by r, while you multiply each of its components by r. And the advantage of all this is that we can take linear combinations, and that's the key in this course. We can take linear combinations of vectors 3 times 1, 2, minus 2 times 0, 1. And when you do 3 times 1 minus 2 times 0, you find yourself at 3. When you do 3 times 2 minus 2 times 1, you find yourself at 4. So these definitions on the top half of the slide enable me to do linear combinations as the example on the bottom half of the slide. One advantage of the matrix notation is when you write these systems down, there's a lot of sort of writing x's and y's and equal signs, and we can get rid of all that just by writing the numbers themselves, the minus 3, the 0, the 2, and that's what I have here. So I can turn this system in. Into what's called here an augmented matrix. The vertical bar makes it augmented. By just simply writing down the real number coefficients on the left of the vertical bar and the constants on the right of the vertical bar. The vertical bar just reminds me that the ones on the left and the ones on the right are a little different. Do Gauss's method, the same Gauss's method steps as we've been doing for so long. This is obviously echelon form, and it so happens to be the case you see that there is a row with X leading, there's a row with Y leading, but there's no row with Z leading, so we know that there's going to be infinitely many solutions. And we see the two equations on this. This abbreviates the two equations. Minus 3x plus 2z equals minus 1. There we go for the top. And minus 2y plus 8/3 z equals minus 2. There we go for the bottom. There's no reason why I can't take those two equations and do what I've been doing before, which is to parameterize. That is to say, take z and use it as the variable with which you express the other variables. So you express x in terms of z and y in terms of z, and you end up with this three equations here. X is expressed in terms of z, y is expressed in terms of z, and it's a little silly, but z is expressed in terms of z. That gives me this solution set, and I wrote it in vector notation here. The vector notation is very nice here because it organizes the constants, the 1/3, the 1, and the 0, all in one place, and the coefficients of z, the 2/3, the 4/3, and the 1, all in one place here. So this is an especially organized way to write down the information that is here. And it's awfully nice because right away we see, for example, what happens when you plug in different z's. If you plug in a 0 or a 1 or a 2 or a -1/2 for z, you get the whole family of solutions, the whole family of XYZs written out there very plainly. So this is an organized way to write this. Just a nice way to write this. Just to have a second example, there's nothing special about this example so much, just a simply different example illustrating the same thing. Here's a the system, and I can write it in this augmented matrix form. When you do Gauss's method there, you
So the first one, if a system has four variables but only three independent equations, how many free variables does it have? It's supposed to be one. What would happen if two rows were all zeros? How many free variables would that create? Two. How can you tell at a glance how many free variables a system has from the zeros, from like the vector zeros? Uh, Please give me the answer for the last.
get echelon form, and you convert it to this, to this way of writing the solution set, the way of writing the infinitely many different vectors that all solve this system, infinitely many different x, y, z, w's that all solve this system I started with. You see there is a z times and a w times. And there's also some constant is infinitely to the echelon, these written out there very plainly. So this is an organized way to write this. Just to have a second example, there's nothing special about this example so much, just a simply different example illustrating the same thing. Here's a system, and I can write it in this augmented matrix form. When you do Gauss's method there, you get echelon form, and you convert it to this way of writing the solution set, the way of writing the infinitely many different vectors that all solve this system, infinitely many different x, y, z, w's that all solve this system I started with. You see there is a z times and a w times, and there's also some constants. So it's again the advantage of this of this particular notation is that it shows the constants isolated, the coefficients of z isolated, and the coefficients of w isolated. So it's an organized way of doing the job that we've been doing so far already. Okay, then so the next section.
The fundamental, root of it all building block for linear algebra is the vector. The fundamental, root of it all building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see, broadly speaking, there are three distinct but related ideas about vectors, which I'll call the physics student perspective, the computer science student perspective, and the mathematician's perspective. The physics student perspective is that vectors are arrows pointing in space. What defines a given vector is its length and the direction it's pointing. But as long as those two facts are the same, you can move it all around and it's still the same vector. Vectors that live in the flat plane are two-dimensional, and those sitting in broader space that you and I live in are three-dimensional. The computer science perspective is that vectors are ordered lists of numbers. For example, let's say you were doing some analytics about house prices, and the only features you cared about were square footage and price. You might model each house with a pair of numbers, the first indicating square footage and the second indicating price. Notice the order matters here. In the lingo, you'd be modeling houses as two-dimensional vectors, where in this context, vector is pretty much just a fancy word for list, and what makes it two-dimensional is the fact that the length of that list is 2. The mathematician, on the other hand, seeks to generalize both these views, basically saying that a vector can be anything where there's a sensible notion of adding two vectors and multiplying a vector by a number, operations that I'll talk about later on in this video. The details of this view are rather abstract, and I actually think it's healthy to ignore it until the last video of this series, favoring a more concrete setting in the interim. But the reason I bring it up here is that it hints at the fact that the ideas of vector addition and multiplication by numbers will play an important role throughout linear algebra. But before I talk about those operations, let's just settle in on a specific thought to have in mind when I say the word vector. Given the geometric focus that I'm shooting for here, whenever I introduce a new topic involving vectors, I want you to first think about an arrow, and specifically, think about that arrow inside a coordinate system, like the xy plane, with its tail sitting at the origin. This is a little bit different from the physics student perspective, where vectors can freely sit anywhere they want in space. In linear algebra, it's almost always the case that your vector will be rooted at the origin. Then, once you understand a new concept in the context of arrows in space, we'll translate it over to the list of numbers point of view, which we can do by considering the coordinates of the vector. Now, while I'm sure that many of you are already familiar with this coordinate system, it's worth walking through explicitly, since this is where all of the important back and forth happens between the two perspectives of linear algebra. Focusing our attention on two dimensions for the moment, you have a horizontal line, called the x-axis, and a vertical line, called the y-axis. The place where they intersect is called the origin, which you should think of as the center of space and the root of all vectors. After choosing an arbitrary length to represent 1, you make tick marks on each axis to represent this distance. When I want to convey the idea of 2D space as a whole, which you'll see comes up a lot in these videos, I'll extend these tick marks to make grid lines, but right now they'll actually get a little bit in the way. The coordinates of a vector is a pair of numbers that basically gives instructions for how to get from the tail of that vector at the origin to its tip. The first number tells you how far to walk along the x-axis, positive numbers indicating rightward motion, negative numbers indicating leftward motion, and the second number tells you how far to walk parallel to the y-axis after that, positive numbers indicating upward motion, and negative numbers indicating downward motion. To distinguish vectors from points, the convention is to write this pair of numbers vertically, with square brackets around them. Every pair of numbers gives you one and only one vector, and every vector is associated with one and only one pair of numbers. What about in 3 dimensions? Well, you add a third axis, called the z-axis, which is perpendicular to both the x and y axes, and in this case, each vector is associated with an ordered triplet of numbers. The first tells you how far to move along the x-axis, the second tells you how far to move parallel to the y-axis, and the third one tells you how far to then move parallel to this new z-axis. Every triplet of numbers gives you one unique vector in space, and every vector in space gives you exactly one triplet of numbers. Alright, so back to vector addition and multiplication by numbers. After all, every topic in linear algebra is going to center around these two operations. Luckily, each one's pretty straightforward to define. Let's say we have 2 vectors, one pointing up and a little to the right, and the other one pointing right and down a bit. To add these 2 vectors, move the second one so that its tail sits at the tip of the first one. Then, if you draw a new vector from the tail of the first one to where the tip of the second one now sits, that new vector is their sum. This definition of addition, by the way, is pretty much the only time in linear algebra where we let vectors stray away from the origin. Now, why is this a reasonable thing to do? Why this definition of addition and not some other one? Well, the way I like to think about it is that each vector represents a certain movement, a step with a certain distance and direction in space. If you take a step along the first vector, then take a step in the direction and distance described by the second vector, the overall effect is just the same as if you moved along the sum of those 2 vectors to start with. You could think about this as an extension of how we think about adding numbers on a number line. One way that we teach kids to think about this, say with 2 plus 5, is to think of moving 2 steps to the right, followed by another 5 steps to the right. The overall effect is the same as if you just took 7 steps to the right. In fact, let's see how vector addition looks numerically. The first vector here has coordinates 1, 2. And the second one has coordinates 3, -1. When you take the vector sum using this tip-to-tail method, you can think of a 4-step path from the origin to the tip of the second vector. Walk 1 to the right, then 2 up, then 3 to the right, then 1 down. Reorganizing these steps so that you first do all of the rightward motion, then do all the vertical motion, you can read it as saying, first move 1 plus 3 to the right, then move 2 minus 1 up. So the new vector has coordinates 1 plus 3 and 2 plus -1. In general, vector addition in this list of numbers conception looks like matching up their terms and adding each one together. The other fundamental vector operation is multiplication by a number. Now this is best understood just by looking at a few examples. If you take the number 2 and multiply it by a given vector, it means you stretch out that vector so that it's 2 times as long as when you started. If you multiply that vector by, say, 1/3, it means you squish it down so that it's 1/3 the original length. When you multiply it by a negative number, like -1.8, then the vector first gets flipped around, then stretched out by that factor of 1.8. This process of stretching or squishing or sometimes reversing the direction of a vector is called scaling. And whenever you catch a number, like 2 or 1/3 or -1.8, acting like this, scaling some vector, you call it a scalar. In fact, throughout linear algebra, one of the main things that numbers do is scale vectors, so it's common to use the word scalar pretty much interchangeably with the word number. Numerically, stretching out a vector by a factor of, say, 2, corresponds with multiplying each of its components by that factor, 2. So in the conception of vectors as lists of numbers, multiplying a given vector by a scalar means multiplying each one of those components by that scalar. Given vector of, say, changeably with the word number. Numerically, stretching out a vector by a factor of, say, 2, corresponds with multiplying each of its components by that factor, 2. So in the conception of vectors as lists of numbers, multiplying a given vector by a scalar means multiplying each one of those components by that scalar. You'll see in the following videos what I mean when I say that linear algebra topics tend to revolve around these 2 fundamental operations, vector addition and scalar multiplication. And I'll talk more in the last video about how and why the mathematician thinks only about these operations, independent and abstracted away from however you choose to represent vectors. In truth, it doesn't matter whether you think about vectors as fundamentally being arrows in space, like I'm suggesting you do, that happen to have a nice numerical representation, or fundamentally as lists of numbers that happen to have a nice geometric interpretation. The usefulness of linear algebra has less to do with either one of these views than it does with the ability to translate back and forth between them. It gives the data analyst a nice way to conceptualize many lists of numbers in a visual way, which can seriously clarify patterns in data and give a global view of what certain operations do. And on the flip side, it gives people like physicists and computer graphics programmers a language to describe space and the manipulation of space using numbers that can be crunched and run through a computer. When I do mathy animations, for example, I start by thinking about what's actually going on in space and then get the computer to represent things numerically, thereby figuring out where to place the pixels on the screen. And doing that usually relies on a lot of linear algebra understanding. So there are your vector basics, and in the next video, I'll start getting into some pretty neat concepts surrounding vectors, like span, bases, and linear dependence. See you then! The fundamental root of it all building of it all building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see, broadly speaking, there are three distinct but related ideas about vectors, which I'll call the physics student perspective, there are three distinct but related what exactly a vector is. You see, worth making sure that we're all on the same page about what exactly a vector is. You see, block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see,
Should we play the song for him, Josephine?
Oh, yes, please. Play that tune.
Don't make me play it for you, Reese. I'm good. This one's for you, yeah? Not today. Come on, dig deep now. You love it, Reese. We love it. Come on. Yes, Reese.
Chceš se zapojit do soutěže o zájezd do Dánska? Tak o ničem nepřemýšlej a kup alespoň 2 sušenky Opavia.
Constants. So it's again the advantage of this particular notation is that it shows the constants isolated, the coefficients of z isolated, and the coefficients of w isolated. So it's an organized way of doing the job that we've been doing so far already. Okay, then so the next section is going to be noticing something about that particular way of writing the solution set, and we'll see you then next time. Very nice, and there we go. Okay, bye-bye.
Homogeneous.
Hello. Hi. Hello. Okay, last time we talked about solving a linear system, finding the solution set description using matrix and vector notation.
Your student or professional looking to study something new, there are now a bunch of great AI apps that can help you out. I reviewed a ton of apps, but these are the 8 best AI apps for studying. Okay, let's start with Traverse, a unique visual note-taking app that combines the best features of mind mapping, flashcards, and bidirectional linking. So what sets Traverse apart is its approach to organizing information. You can create multiple whiteboards called Traverses, each dedicated to a specific topic, book, project, or class. And within each traverse, you can create notes and place them on the board, jotting down ideas or concepts you're learning. But here's where it gets interesting. Traverse lets you create flashcards for each note. You can either use the new flashcard button or simply highlight the text you want to memorize. Personally, I find this easier as on time, making it easy to squeeze in some study sessions throughout your day. It's not as smooth and easy to use as Anki, but
There's only a few good resources that really help you learn the math for machine learning. Learning mathematics can be very intimidating, and I have been through this. So I want to show you some of the best resources that help me, and I hope that it helps you too. I've looked at factors like how much these resources cost, how accessible it is, the quality of teaching, do they have exercises that will help you reinforce the concepts that you learn, and most importantly, how easy is it to understand the difficult concepts? Like, for example, do they use illustrations to explain these complex concepts? I reviewed resources resources ranging from textbooks all the way to online courses and including some YouTube videos. However, one thing that I didn't review is the workshops because number one, workshops are hard to access. You have to sit through the entire workshop, and not to mention you probably have to pay for it. And there's just too many of them. In the end, I will reveal the best resource that I would prefer if I had to start from scratch all over again. So stay tuned for that. I also want to know which of these resources you would prefer, so let me know down below after you see this entire list. Before I reveal all of them, I want to mention that some of the resources explain, but they also have videos on the Mathematics for Machine Learning Specialization by Imperial College London. Overall, I think that this course is well structured to learn linear algebra and multivariate calculus, but it stops short of teaching statistics and probability theory, so you will need to find a separate course for that. I do like the video's style of teaching, but I think the exercises are not rewarding enough, and they don't seem to have a forum to discuss and ask questions. The second resource is also on Coursera, but I think this is a way better course for two specific reasons. Of course, I'm talking before you begin the course. They also have programming exercises that will.
Hi, and welcome to this overview of DeepSeek. Thanks for your interest in learning more about this AI tool. I help review AI tools like this one, and DeepSeek is pretty exciting. DeepSeek is an AI platform that gives you access to powerful models for all kinds of tasks. The main things people use it for are coding help, math problems, logical reasoning, and text work. How flexible or have a few different products. Their newest V.
Hi everyone! I've heard a lot of people are now using ChatGPT to help them solve math problems. So today, we will put ChatGPT to a test. We will compare the math problem solving abilities of ChatGPT with several strong math solving apps on the market. They are
all you need to learn machine learning in.
What if I told you that the perfect study buddy isn't human at all? What if I told you that the perfect study buddy isn't human at all? Hey everyone, today I'm showing the 10 most powerful AI study tools that are revolutionizing education in 2025. These aren't just your basic chatbots. We're talking about First up, sort of revolutionary, using advanced neural networks to understand exactly how you learn and where you struggle. Think of it as having a genius professor who's available 24/7 and teaching style in real time. Whether you're a visual learner or prefer hands-on examples, it adapts to match your style perfectly. Pricing starts with a surprisingly robust and retain information.
We're at that stage with AI tools where they want you.
You want to become a data scientist or machine learning engineer at school. When I started today, and I'll also share some functions, you'll know whether to adjust your learning rate, try a different optimizer, or tweak your data processing. Or, I'm a huge fan of StatQuest for personal use. It covers key topics we've already discussed, engineering concepts, so they're super fun. I can't say the instructional quality is like have manga math books. So I've read the Manga Guide to Calculus, Manga Guide to Linear Algebra, and Manga Guide to Statistics. They also have Statistics for Machine Learning ebook by Deisenroth and colleagues.
There's only a few good resources that really
And this time I want to give some justification for that. I want to explain why we're so keen on matrix and vector notation. In particular, it enables us to characterize the solution set of the linear system. We can completely understand what solutions look like. Okay, so let's start off by backing up to the previous slide. That's the slide that we showed in the last video at the end. We had a linear system like so. We did Gauss's method like so. We came up with a complete solution set written in vector notation. And you notice that it has really two parts. There's a part of a vector of constants, and you also notice that the remainder of the solution set has something associated with z, something associated with w. So there's vector times letter, vector times letter. We want to show that every solution set can be written in that form. Particular here, this is called. Homogeneous here, this is called. So there'll be a vector of constants and then also some letter times vector, letter times vector, letter times vector. Okay. Okay. So I want to describe that looking at the form of the solution set. So here is just like the previous one that I just showed you a second ago. Here is a system. Gauss's method gives you some answer, gives you echelon form. You take the echelon form, you put like so. And now I want to ask you to notice something about those. If you take z and w, you can take them to be anything you like, they're free. If you take z and w to be 0, well, then this part 0, this part 0, and you just get the vector of constants, the 12/5 for x, the minus 1/5 for y, the 0 for z, and the 0 for w. That is to say that this vector here in the solution set is a particular solution of the original system. That if you plug in 12/5 for x and minus 1/5 for y and 0 for z and 0 for w, you'll get 2. And if you plug in 12/5 for x and minus 1/5 for y and 0 for z and 0 for w, you'll get 5. So this is a particular, this one here is a particular solution of the linear system. So we can understand this solution set in some way by understanding the parts, and we're starting off by understanding the part of that very first part, the vector of constants. Okay? To understand the rest, to understand the vector times a letter stuff, I want to isolate on a particular kind of, on a special kind of linear system. I want to take those, the constants on the right-hand side, the constants over here on the right-hand side, the 2 and the 5, I want to take them and change them into zeros. If you change the 2 and the 5 into zeros, then what you get is a system that is simpler in the following sense. I can tell at a glance that it has the solution x equals 0, y equals 0, z equals 0, and x equals 0, y equals 0, z equals 0, w equals 0. So the vector of zeros definitely solves this system. So I know one of the particular solutions of this system. It is the vector of zeros. Gauss's method goes through the exact same particular of zeros. I want to take them in the solution for x and minus 1/5 of constants, the 12/5 for x vector here in the 12, and if you plug your system, understanding the part. Okay. To understand the rest, to understand the vector times a letter stuff, I want to isolate on a particular kind of, on a special kind of linear system. I want to take those, the constants on the right-hand side, the constants over here on the right-hand side, the 2 and the 5, I want to take them and change them into zeros. If you change the 2 and the 5 into zeros, then what you get is a system that is simpler in the following sense. I can tell at a glance that it has the solution x equals 0, y equals 0, z equals 0, and x equals 0, y equals 0, z equals 0, w equals 0. So the vector of zeros definitely solves this system. So I know one of the particular solutions of this system. It is the vector of zeros. Gauss's method goes through the exact same steps, and you end up with a solution set that I didn't bother to write the vector of zeros. So I have vector times a letter, vector times a letter. So this is the other half of the general solution. Back here I had a general solution that had a vector with some constants in it, and then vector times a letter, vector times a letter. Well, here I've managed to isolate on the vector times a letter stuff by turning those into zeros. So, in general, when you look at a linear equation like the top line or the bottom line here that has a 0 on the right-hand side, you say that a linear equation is homogeneous if it has a constant of 0. So it has a 0 on that right-hand side. Homogeneous. And of course, the system is homogeneous if it has all zeros on the right-hand side. Now, homogeneous systems are linear systems. So they're just like other linear systems, except they have one special property. The homogeneous system can have infinitely many solutions. Look at this one here, has infinitely many solutions. homogeneous system can have a unique solution. This one here has a unique solution. But we know one of the solutions for a homogeneous system is all zeros. For example, if you plug x equals 0, y equals 0, z equals 0, you definitely get one of the infinitely many. If you plug x equals 0, y equals 0, z equals 0, you get the one solution here. So that is to say that homogeneous systems are linear systems, but they cannot have the no solutions possibility. That can't happen with a homogeneous system. Oops, I spelled solution wrong. Whoops. Okay, so in general, if you have a homogeneous system, then the solution set has to look like this. Vector times a letter, vector times a letter, vector times a letter, however many you've got. It's how many will you have? It says k is the number of free variables. So when we had z and w for free variables, why we had 2 vectors. Now, I'm going to do something here that we do sometimes. Rather than give a proof for the lemma, proof is in the book, but rather than give a proof for the lemma, we're going to try to convey the idea here of the proof by giving an example. Of course, you should refer to the book for the proof. That's the right thing to do. So I want to instead convey the idea of the proof, since the slides are intended to introduce the discussion that's in the book. Okay, so for the main idea here, you consider this system of homogeneous equations, and using the bottom equation, you can express y in terms of z and w. Okay, that's fine, but notice that when you do, there's no constants, or a constant of 0, whichever way you like to say it. If you take the value of y and you substitute into the top equation, again, no constants, or a constant of 0, whatever way you like to say it, and so you get x expressed in terms of z and w with no constants. So you end up with no constants, or a constant of 0. So you end up with z times a vector, w times a vector, no vector of constants, or again, a particular solution of the 0 vector. And then this right here, minus 2, 1, 1, 0, that's the beta 1. And 0, minus 1, 0, 1, that's the beta k, if the k is 2 in the case. So we have that the general solution can be written as vector times a letter, vector times a letter, vector times a letter. Okay, so the homogeneous solution set is special in some way, that we have a characterization of how you can write it, and that stems from the fact that when you have a homogeneous system, the particular solution is there is a particular solution that is the 0 vector. Okay, so in general then, for a linear system in any particular solution, P, the solution set, it looks of this form, P plus H. If you give me a linear system, I can write its solution set in this form, where H satisfies the associated homogeneous system and P is any particular solution. Now this one we are going to prove. I am going to go through the argument. It's not very long, but it involves 2 steps. This says that the set of solutions can be written in this form. Set of solutions equals this set here, where P is any particular solution. So this is 2 sets, a set of solutions and this set here. To show that 2 sets are equal, the most straightforward thing to do, not the only thing to do, but the most straightforward thing to do, is to show that each one is a subset of the other. And that's what we're going to do here. To give the proof, I couldn't fit it all on one slide, so it's on the second slide too. But to give the proof, I'm going to show, first of all, that if a vector is in the solution set, then it is in this set also. And then on the second slide, I'm going to show that if a vector is in the set given, the P plus H set, then that vector solves the system. So that's called mutual inclusion. I'm going to show set inclusion both directions. If a vector solves the system, then it's of this form. Okay, so to show that, what do I have to do? Well, you assume that S solves the system. So then I want to show that S minus P is the right form for H. If I show that S minus P equals H, why then S equals P plus H. Okay, so what is H? H means that when you plug the components of the vector in, then you got to get 0. That's what homogeneous system means. Okay, so I'm taking the components of S minus P,